afternoon, good evening, everyone. Those who have joined this webinar on IBPSA platform. I welcome all of you, and I'm very happy to state that this is a 10th edition of webinar in the series. As you know, that webinar is based on a book edited by Roberto Lombard and Jan Henson, which is endorsed by IBPSA. The title of the book is Building Performance Simulation for Design and Operation of Buildings. I'm glad that today Dr. David Claridge has decided to offer us a webinar. I'm glad that he's spending time for us. Professor Claridge is Leland Jordan Professor of Mechanical Engineering, and he's also a Director of Energy Systems Laboratory at Texas A&M Engineering Experimentation Station. We will have this webinar, and he will deliver a lecture, which will be followed by question and answers. If anybody wants to send a question, I would request them to use a question pane. All attendees are on mute right now. You send your question using a question pane on GoToWebinar panel. I will be able to moderate that, and at the end of the session, we'll have question and answer sessions. So with this introduction, I am again inviting all of you, and I welcome all of you, and over to Professor David Claridge.
Well, I guess I'll say good day because we have people from all different parts of the day on the webinar, I'm sure. I'd like to start by giving just a bit of an explanation for my title. I've said use of calibrated simulation for practical optimization of building operation. And I put that word practical in there because very often if we use the term optimization, why people may expect that we are using an objective function and doing an optimization in that fashion. And when we talk about improving and optimizing the operation of buildings, why we seldom get to that level. And so we're talking about it more from the standpoint of improving it to make it as good as we can do it in a practical sense. I'm not going to assume that all of you are familiar with the existing building commissioning process, so I want to give a little bit of an overview of that since I'm going to be talking today in the context of that process. It is something that is known by various terms. Existing building commissioning is the term that ASHRAE has adopted. Retro commissioning is widely used. Internally, the process that we developed starting about 30 years ago, before I had ever heard the term the term existing building commissioning or retro commissioning, is continuous commissioning, and that is basically our internal laboratory version of these processes that are now known by these more generic names. And so we will be talking about it within the context of the process that we use internally here. And you know, on this slide, I'm simply saying that calibrated simulation is rapidly becoming an important part of it. It certainly has not been a significant part of the commissioning process historically, but as the calibration process itself becomes either automated or nearly so, why it becomes much more practical to use it when you're talking about doing something rapidly in the field. If I look at the different facets or phases of the existing building commissioning process, we have two major phases, one of which is to conduct investigation at multiple levels and then to actually implement measures that have been identified during the investigation phase. And that investigation phase is, in our process, is broken down into several individual steps as well, because the first thing we want to do is figure out whether it's worth sending someone into a building. So that's what we call the opportunity assessment, which is performed remotely. Then the detailed assessment is performed on site, and if the building owner decides at that point to fund the implementation of the process, why then we go forward to develop the performance baselines and spend a lot of time on site developing a detailed implementation plan. After approval by the owner and the owner's staff, why the measures are implemented. Critical part of the process is to train the staff on the measures implemented so that they don't immediately undo them. And then certainly one wants to document the changes that have been implemented in terms of whether it's improving energy performance or whether it's improving comfort, both. And then afterward, it's a good idea to perform some tracking and something that we refer to as ongoing commissioning to make sure that the process continues to work. Just to give an idea of the kind of results that can be achieved by this process, our experience in dozens, if not hundreds of buildings that we have worked in are that we will typically reduce the energy cost by 10 to 20%. And the process typically is not installing any new equipment. So we're talking, the investment is basically in the engineering time that goes into the process, along with any basically deferred maintenance that is discovered that is causing major inefficiencies, and this is often significant. But with that said, we typically will see a return on that investment of 35% to as much as 100%. And we've had some cases where it's been even higher than that, i.e. the payback has been less than 1 year. And improved comfort is often achieved at the same time. Not always, but we have found over the years that if a building has a persistent comfort problem, that very often is something that has had attempts to resolve it that have resulted in some substantial inefficiencies in the operation of the building. I'll just show one result from one of our projects that's been going on for some time. I show it for two reasons. One, the site is one that I expect will be at least not totally unfamiliar to many people. And secondly, it was a very successful project. This is not a typical project. It's been more successful than the average, but we've been working with the Dallas-Fort Worth International Airport, which is based on aircraft departures and landings. I believe is one of the 10 largest airports in the world. And over that period of time, we have helped them to save over $20 million in their operations, and their expenditures to achieve that savings have been less than $4 million. So it has been a very good project from their perspective. As I said, this is not typical. Our typical is somewhat smaller than that, but you know, we all like to talk about success stories. So, okay, but now I'd like to move on to look at how we can use calibrated simulation in the process of implementing these improvements. Oops, I need to push a different button here. So let's, well, what has happened? Oh, there we go. Try that. Suddenly, oh, here we go. That'll work. There we go. Okay. What I have done in this slide is taken all these different stages of the existing building commissioning process, and I have bold-faced the ones where we have found that calibrated simulation can play a role, and then, of course, noted that. So we have what we call the opportunity assessment. We'll talk about that in some detail. And in the detailed assessment, where we can use calibrated simulation, developing performance baselines, detailed implementation plan, and then documenting the savings and the ongoing commissioning aspects of it. So let's start off with the opportunity assessment phase. This is indicated earlier, is the phase where we don't want to send someone on site. This may not be a big deal if it's a local site, but well, just let's say Dallas-Fort Worth Airport, which is one of our major customers. I mean, they're not a long ways away. They're about a 3-hour drive, but three hours of engineering time to drive up and drive back is a significant investment if there's not going to be an opportunity. And so we have developed a way in which we use calibrated simulation here. Historically, I can remember many times that I would look at the energy bills for a building, and from that do some spreadsheet analysis to see whether it looked like, you know, in the patterns of use there were some opportunities there. A lot of people like to look at this information and look at an energy cost index or an energy use index and say, well, if it's higher than norms, why, that's a good opportunity. But that doesn't take into account anything to do with the systems in the building or the uses in the building. And so what we have now come up with is we've developed an internal tool that we call Opportunity Assessor that performs a simulation on a building before we ever get there using some very limited information. We take the utility bills, as we've illustrated here, ask some simple questions that any building mechanic could answer without looking anything up, and then come up with a rough estimate of the potential operational savings that could be there. And this is not intended to be what I would call an accurate estimate. It's not intended to be, say, it's going to be 13% plus or minus 1. It's intended to say, okay, if it's saying 13%, why, we would expect that that says that the savings probably will range between, you know, half of that and twice that. But it gives us some kind of an indication based on the physical characteristics, some very rough physical characteristics of the building and its systems, and its measured energy consumption, what kind of inefficiencies may be present. And if it's a good opportunity, why, then we go on to do a site investigation. And the WinAm mentioned here is our specific simulation tool that we use there. If not, why, I mean, then we may say, well, you know, particularly if you've got a building owner that has several buildings, well, let's look at a different building first. But let's talk a little bit more about how we specifically use that calibrated simulation in this opportunity assessor. What it does is it uses an automated calibration from the information it's given to create typically several dozen different calibrated models for the building, starting from different sets of input assumptions, since we have very rough information on the characteristics of the building. Then each of those calibrated models is examined automatically, and various operational improvements are added in to see what particular changes in the parameters, what kind of savings would result from them. And then, since we have, you know, several dozen different starting points, and hence presumably several dozen different savings estimates, why, we come up with that with a rough approximation to the level of savings that we might achieve in a particular building. And I'm going to show you a particular example to perhaps help you understand more clearly the kind of results we may get. Here we have a picture of one of the local middle schools, basically grades 6 through 8. And we looked at this building actually with some students in a course that I did earlier this year. And if we look at the inputs that we use, you notice we say, okay, what kind of cooling do you have in the building? Okay, we said that we've got an on-site chiller, no more information than that. does this cooling system provide cooling to any other buildings that aren't on that same meter? Well, before we got there, we didn't know. What kind of heating? Well, they told us it was hot water, and there was an on-site boiler. And this slide has an error down there because it says is chilled water provided to any other buildings. That should be as hot water provided to any other buildings. We said, we're not sure. They said, yeah, there are parking lots, and so there's outside lighting on these parking lots. Didn't say anything about how much. The building has 144,000 square feet of floor area on 2 floors. It's a school. It has grades 6 through 8 there. How much window area? Well, we didn't know. We had that picture, so we just said it's average. Window types, we didn't know that. They did tell us that it had single duct VAV air handling systems in the building. And that was basically the information that we had in terms of the systems in the building. So you can see it's not information that required a high level of detail. It's something that anybody could answer from a simple question. I mean, anyone familiar with the building could answer very quickly. Then in addition to that, we had a year of utility bills. In this case here, the electric bills for the school for a year. And you can see that those are running generally between $10,000 and $20,000 per month. We use that. We also use the gas bills, which are much smaller in this case. They basically provide heating in the building, and we don't have a lot of heating requirements here. And so that information was taken, in this particular case, why the program developed 49 different calibrated simulations based on the uncertainty in the information given. For example, we said it had average window area, and so it started off using a variety of different window sizes, assuming that you had at one end about 15% and going up to 40% window area from an initial simulation, and then going through a calibration process. The mean of all of the savings estimates was that there was probably about 5% potential savings from some simple operational improvements in this building. And just to give you a little bit more idea, the same group at the same time, we were doing a total of 3 schools of the local schools, and the savings estimates that we got ranged from 5 to 16% for these 3 different schools. And that kind of thing would basically say, okay, if we were going to only do one, why we would probably go to the high school based on this information. But we certainly don't expect this to tell us that we're going to achieve 3 times as much savings in one school as the other for starting points. Okay, now we get to the detailed or the on-site commissioning assessment and our use of calibrated simulation there. Calibrated simulation, certainly as I indicated in the chapter, the earlier version of the chapter, is a process that historically has taken a lot of time. I can remember 20 years ago, one of my colleagues had a student who did their master's thesis creating a calibrated simulation of a single building. Obviously, you're not going to put that kind of time and effort into a calibrated simulation that is going to be looking for a few $1,000s worth of savings in a building. And since then, why there have been a lot of procedures developed. The earlier version of the chapter has a procedure that we've used for some time that is a fairly organized procedure that helped us reduce the calibration time from this thesis length down to, let's say typically it was getting us down to at least a few days. And now we have moved on to, we've chosen not to actually implement an automated process for are detailed assessments, because the automated process is typically one where where you may get some inputs that don't make a whole lot of sense for a particular building. And we would like to have the engineer who is doing the simulation be able to apply their knowledge of the building to the specific building, so that the calibrated simulation that is created doesn't have any really obvious flaws. And so the process that we've set up within our internal implementation is one where the engineer puts in a number of inputs. The program then goes through and evaluates how much the particular error metrics that are used to evaluate the goodness of calibration will be improved by making a variety of changes in the inputs, and then it takes those changes and rank orders them in the table at the bottom of this slide. Why, you probably can't see all of those individual measures, but it ended up saying in this particular case that if the minimum airflow were changed in this case from 0.8 to 0.26, why it would reduce the error, the overall error metric, from 112% to 15%. There are a number of others below that that would have smaller impact on it. And so normally one would look at that and say, okay, let's change the minimum airflow to the value that it recommends there, if we don't have any reason to believe that it couldn't be done in that building, or that the building couldn't be operating in that fashion. And so that would be done, and then it will repeat these changes and tell you if you change something, how much it would improve that. And you go through that, which typically will actually only take you perhaps 5 minutes, and you have a calibrated simulation that doesn't have any obviously bad inputs. And I want to go ahead and illustrate, I mean, we've gotten so that we will often use this process before we get to a building to basically help guide us in what we're going to actually look at. And what I've shown here I've shown a picture that I got off of Google Maps 2 or 3 years ago, when before we went to visit a particular site. I had a little bit of information about the systems in the building. I didn't know anything about the physical details, and so I used this picture to give me some idea of what kind of window area it had, and even the number of floors in the building. And then before I arrived on site, I developed a calibrated simulation based on that model, and it was very interesting to me that while this building, the information we had was that it had variable air volume systems in the building, the minimum flow settings that gave the best calibration were about 80% of maximum flow. It also had an economizer in the building, and it indicated that the economizer seemed to be operating as if it had a maximum outside air intake of about 25%. That gave us a couple of things to concentrate on when we got to the building. The first one being looking at the air handler VFD settings, and what we found was that all but one VFD in the building were between 75 and 100% of maximum speed, and that half of them were above 90%. So that original calibrated input was very consistent with the way the building was operating. I won't go into the details. I mean, there were a number of things that were wrong with the way the terminal boxes were operating. And in fact, I mean, this was a major opportunity for efficiency improvement in this building. It was also interesting that when we looked at the economizer, it was a waterside economizer, and we discovered that while it was being used routinely, this water side economizer, even when operating at flat out, and when there was a 10-degree delta T in the cooling tower, why there was some kind of a flow restriction that nobody was aware of that reduced the flow into the heat exchanger to the point that it was only achieving about a 1-degree delta T on the chilled water side. I cite this as, again, good or let's say maybe unusual examples of how well the calibration process can tell you something about what's happening in the building, but certainly we have had other experiences as well where it has ended up giving us some good guidance in terms of what to look for when we get to the building. So now I'm going to simply move on and more or less state the kind of results that we got. In one of the schools that we looked at, this was one where we had opportunity assessor was saying there was the potential for about 16% savings. When we did site visits, looked at the EMCS screens, and then evaluated the measures that we saw that we found could actually be implemented in the building. Why we ended up with 11% savings. This is total energy cost for the building as the potential from implementing some rather simple measures in the building. Now let's move on to talk briefly about the use of calibrated simulation in the detailed implementation plan. The commissioning process is one where once the on-site assessment has been done and the decision has been made to go forward, why typically the engineers will spend substantial time getting down to taking measurements at individual terminal boxes, things like that, before they develop the actual measures that they will recommend for implementation, which will then be reviewed with the site staff and approval obtained before they're implemented. But one of the things that's very useful here is that once you have that calibrated simulation model from the assessment, you can basically take that model and refine it based on your findings from more detailed measurements and your site visits, and you come up then with a what we might say is a site verified calibrated simulation model, and we have our program set up so that we can then input into it basically any kind of operational changes that we want. Here I just have an illustration of several for one site, and it becomes very useful then when you get to your implementation plan, because you now have a detailed information on how much savings will be produced from individual measures. We typically don't like to provide this information to the client at an early stage. We certainly want to do it at a late stage, and in this particular case, why changing the chilled water supply temperature appears that it would have a negligible savings, and hence this ends up helping the engineers decide where they're going to put their time and effort in implementing measures. Because you may sometimes have a measure that will take a lot of implementation time and not provide nearly as much savings as some other measure that will provide possibly even more savings. Now let's move on to the question of calibrated simulation in M&V. So their performance baselines can be developed using calibrated simulation. And in fact, if we look at the International Performance Measurement Verification Protocol, why it permits the use of calibrated simulation, likewise ASHRAE Guideline 14 has calibrated simulation as one of its baseline methodologies. The thing that I very much like about the use of calibrated simulation in this case is that it permits you to have a strong physical basis for adjusting your baseline if there are changes in anything like building schedule or the use of a particular portion of a building, or you end up changing out a piece of equipment in a small part of the building. All of these things that the typical regression baselines are really incapable of dealing with. With calibrated simulation, you can handle them very readily. Historically, the cost of calibrated simulation baselines has been high enough that they haven't been widely used. We're starting to see more interest in that area. In fact, within the past year, we had our first M&B project where we had a calibrated simulation requested. In this case, it was based on some changes made to a chiller plant. And right now we have 3 large hospitals that we will be working on where the client has requested us to use calibrated simulation as the baseline for M&B as we move forward there. And so given the great simplification that has occurred in development of calibrated simulation, why I expect that use to increase as we move forward. Now we can get to what might be the final phase of using calibrated simulation, called ongoing commissioning, basically watching the operation of the building after it's been commissioned to be sure that you maintain the efficiency of operation. And this is another place where, while we have not seen a lot of application yet, it is one where calibrated simulation can be quite useful. I'll talk specifically how we can use it in fault detection and diagnostics, but the example that I'm showing here is one from some of our early work in this area, where we have in the plot in the right-hand corner of the picture, we have what we're showing is basically the blue line is a line that shows the cumulative difference between the measured energy consumption in the building and the calibrated simulated consumption of the building once you have calibrated a simulation to the building after it was commissioned. And in this case, you notice that we got to the point where in November of the particular year here, suddenly things started changing quite rapidly. You notice our units here are millions of BTUs, so if we multiply that by $5 or something as a chilled water consumption is what we're looking at here, over a period of a month, it's turned into several tens of thousands of dollars in unexpected change in consumption. In this case, we had the calibrated simulation. We did not have any diagnostics going on with it, but we had a fairly experienced facility engineer who happened to be a graduate student at the time, was looking at this information, and he ended up concluding that there were 2 things that could account for this change. One was that there was a DX chiller in the building that wasn't hooked up to the chilled water system, and they might have started using it so that the chilled water consumption had gone down. The other possibility that he suggested was that there was some kind of a meter calibration error. When we went to the building with this information and they checked, they happened to have a district chilled water supplier, and lo and behold, to the day where we saw that performance break away, they had come in and recalibrated their chilled water meter. This is probably one of the most dramatic illustration of a change occurring that we have seen, but we have seen other changes where, another example I can cite was one where we concluded that a particular building must have had the outside air pre-cooling unit must have had the temperature set down. When they went and checked, why, lo and behold, the temperature had been dropped from 55 degrees Fahrenheit, where it should have been, down to 45 degrees for pre-cooling. And so we were seeing substantial additional cooling showing up whenever there was a high latent load. Because, I mean, simply cooling the air wasn't causing an issue, but when the latent loads in the outside air got higher, why, it was providing more latent cooling than was required, and that showed up as substantial additional cooling required in the building. Now, when we look at the use of calibrated simulation in ongoing commissioning, we talked about how we can detect changes, and we've moved on from basically doing it by simply looking at deviations between the calibrated simulation and the measured consumption, and have developed statistical criteria. And in this case, I've simply shown a number of faults that we detected in particular buildings using synthetic data, where you see that we can detect changes on the whole building data, changes in outside airflow of 5 or 6%, cooling coil leaving temperature changes of a degree, changes in preheat temperatures, changes in minimum airflow, a variety of things. This is just illustrative, it's not exhaustive, but the point is that these criteria have been also moved on so that we have statistical criteria that can be used to decide whether a change that's being observed is significant and represents a fault, or whether it's just sort of normal statistical variation in terms of the difference between the calibrated model and the actual building operation. And we have also gone on, and I've had a student do work that has come up with a very specific procedure for looking at the patterns in the differences between the calibrated simulation and the measured consumption, and then assigning probabilities to a variety of faults so that when you have no more information than the energy consumption from the building and the basic set points in the building in a calibrated simulation, why, you can get an approximate idea of what the probable cause of the deviation is. So with that, I conclude that calibrated simulation certainly is a very valuable part of the toolbox that we have for performing commissioning in existing buildings, and I'll be glad to take any questions that we may have.
Thank you, Professor. I have received 2 questions so far, and I'll try to unmute Alex Chapin if he can ask question directly to you. Alex, can you hear us? And
yes, can you hear me?
Yes, please.
My question is, are these simulation tools that do the automated calibration available for others to use, or is it only an internal tool that you use on projects?
Okay, the answer is something in between. They're available, but they have been developed used from licensing fees from people who have licensed our process. They're available to licensees. And so it's not something that I can send out the door, but it is something that at this point we have between half a dozen and a dozen private firms that have licensed the process and have access to the tools.
Alex, is that fine? Does it satisfy your question?
Yeah, I think so.
Okay.
I guess to follow up that, can anyone else become a new licensee?
Right. Okay. We have another question from Aloysius D. Cruz, and he wants me to ask question. The question is, what is a typical case where calibration process is unable to mend the gap of simulation.
Is unable to what?
Unable to mend the gap of simulation.
Oh,
So shall I repeat the question?
Let me take one shot at addressing that.
Okay.
I don't know that I can provide a typical case, but our opportunity assessor tool that does automated calibration using very approximate inputs will sometimes conclude that it is, basically it will not converge to a stable point, because we have found over the years in calibrating simulations that you can often get into local minima. And so we do find cases where something will fail to converge, and what we have basically found there is that our initial inputs were simply so bad that the calibration process was unable to get us there. I can't say that you could never have it. Well, I mean, certainly if you have a building that is operating using processes that your simulation tool cannot accurately simulate, why then that will be a case where you may not be able to get good convergence as well.
Okay, thanks, Prof. We have one more question from Mridul Sarkar, and I will repeat the question. Are the initial choice of modification parameters chosen are generic in nature, or varies from building to building and location to location?
Okay, when we look at the modification parameters, we are going to look at them on the basis of what systems are in the building and what parameters do we know, tend to have the most impact in changing consumption in those buildings. Now, when we look, if we're talking about in the calibration process, fundamentally we have programmed a number of changes in where it will end up, certainly if a building has a constant volume system, it will look at different set of modifications than if a building has variable volume system. And if it has district cooling, why it will not look at chiller measures and things like that. But basically in the calibration process within our tool, why we will look at a whole bunch of things since once it's automated. Now, if one does not have the automated tool, the process looks very distinctly at something called calibration signatures to determine which measures you're going to evaluate first.
Yeah, I think yes, I think that does answer a question, and I think we have one more from the same person. Mm-hmm. Is it during the calibration implementation phase, or rather for existing calibration implementation phase, is the project data from certain parameter, for example, construction details are not available, how detailed calibration models are created?
Okay, that's a good question. In terms of construction details, we actually have purposely set our programs up so that they do not require detailed construction details. And because we find that very often the calibration process will conclude that the building is operating differently than the way the construction details told you it should operate. And of course, I can think back an experience or seeing construction details where people said that something was insulated, and you'd put an IR thermography gun on a building and you could see it wasn't insulated, or maybe there were big holes in the insulation, things like that. So that in our experience in the calibration process, particularly for the commissioning process, is that we generally are not highly concerned about detailed building dynamics, but rather longer-term operation over periods of days, and tends to be adequate, and hence we use very limited information about the envelope inputs in these buildings.
Thanks. And we have sort of last question. The Cruz wants to understand that, may I know the simulation engine?
He wants to understand what?
Simulation engine. Which simulation engine do you use?
Okay. Fundamentally, what we are using is a local implementation of a simulation process that was developed by ASHRAE many years ago called the Simplified Energy Analysis Procedure. This procedure has a lot of detail on secondary systems and primary systems, and very little detail on envelope behavior. And we have found this to be definitely the way, we think it's the most efficient way to go when we're dealing with building operational issues, because fundamentally we seldom are concerned about details in the dynamics of the building, and that's why we have gone to the level of basically letting the calibration process tell us what the envelope is behaving like. For example, we end up with an overall UA value for the building, and that is one of the calibration variables that gets varied by the calibration process, but we really never go down to the detail of, you know, what are the individual wall elements.
That's great. Good input, Professor. With this, I think we do not have any further question coming from any other attendees. I wish to express thanks again to you and all those who have joined. Thank you for joining, and I also encourage you to register for IBPSA's conference, which is upcoming in San Francisco in August first week. Please do register and do attend that workshop. Second, next presentation or next webinar would be scheduled on June 22nd, and we will be announcing the details on the website as well as on social media very soon. Thank you for joining. Thank you, Professor, for offering the webinar. Thank you very much.
Thank you all. Enjoyed your questions.
Thank you.